Okay, let's unpack this. Have you ever hit send on an email or, joined a video call and wondered what truly makes the internet work behind the scenes?
Yeah, like what's actually happening.
Exactly.
Yeah.
Or how your Wi-Fi knows which device is yours in a room full of gadgets. Today, we're taking a deep dive into the incredibly intricate world of computer network communication. We're going to peel back the layers, really, to reveal the foundational principles that get your data from point A to point B, no matter how far apart.
It's a fascinating journey, actually. We're going to explore the very language and the rules that allow vastly different digital devices to speak to each other.
Even across continents, right.
Yeah, whether they're across the room or across continents. Our source material, it's a comprehensive collection of notes on network fundamentals, provides us with a kind of roadmap.
Okay.
It helps us understand the ingenious protocols and, well, the clever mechanisms that ensure your data not only arrives, but arrives correctly, efficiently, and often at mind-boggling speed.
So our mission today?
Our mission today is basically to distill the most important insights from these sources, giving you a crystal clear understanding of the unsung heroes of the digital world.
Okay. Sounds good. So to begin, let's establish the absolute bedrock, protocols and layers.
Right.
Think of protocols as the rules of the road for data. I mean, imagine trying to drive without traffic laws.
It'd be chaos.
Complete chaos.
Yeah.
Our sources define a protocol as a set of rules that govern data communications. It's designed to ensure everyone's speaking the same language, defining 3 key elements.
The what, how, and when.
Exactly. The syntax, which is what is communicated, the precise format of the data. Then the semantics, or how it's communicated, the meaning behind those bits and bytes.
And the timing.
And crucially, the timing, when it's communicated, how fast, how often, and in what sequence.
Exactly. And if you look back at early computer networks, they were pretty rigid, weren't they? Often tied directly to specific hardware.
Yeah, very hardware-centric.
But our materials highlight why that approach just doesn't scale for something as vast and dynamic as the internet. The shift to a highly structured, software-based approach built on this idea of network layers was absolutely essential.
Why was that so necessary, though?
Well, it allows for incredible flexibility. It lets us adapt to new technologies without having to, tear down and rebuild the entire physical infrastructure every single time.
Got it. And part of that powerful, structured approach is the concept of network layers. You can visualize it like a multi-story building, maybe.
That's a good analogy.
Where each floor or layer handles a very specific, distinct part of the communication process. For our deep dive today, we're going to focus primarily on 2 foundational layers that really handle the nuts and bolts.
Heavy lifters.
Yeah, the data link layer, which is closest to the physical hardware, dealing with local connections, and the network layer, which is responsible for getting data across entire sprawling networks.
So, if we start at the data link layer, a fundamental question emerges, right? How do we ensure bits sent across a wire are understood and managed effectively? Especially when, that wire isn't perfect.
Nothing ever is.
Exactly. This layer is all about managing the raw physical transmission of data frames. It provides a well-defined service interface to the network layer above it, and crucially, it handles errors and regulates data flow.
Okay, so let's talk errors first. Because those physical communication circuits are, as our sources remind us, not perfect.
Far from it.
Bits can get flipped, signals can degrade. That's where error control comes in. It's a bit like a conversation where you occasionally say, wait, did you hear that correctly?
A check.
Both ends of a connection agree on specific error detecting or maybe even correcting codes. And the receiver actively tells the sender, okay, I got message 3 correctly, but message 4 was garbled.
Right. It needs that feedback. Without that feedback, the sender would just keep transmitting into the void, essentially.
Yeah, throwing data away.
And then there's flow control. This solves a critical problem, preventing a fast sender from completely overwhelming a slow receiver.
Like a fire hose pointed at a drinking straw.
Exactly. Perfect analogy. Our sources describe 2 main approaches here. First, there's feedback-based flow control. This is where the receiver sends information back to the sender, basically giving it permission to send more data based on its current capacity. Like, okay, I'm ready for more.
Yeah.
The alternative is rate-based flow control, where the protocol itself has a built-in mechanism to limit the sender's transmission rate without needing explicit feedback from the receiver. It just knows the limits.
Okay, so how do we actually implement that reliable flow control, especially the feedback part where you need to confirm delivery?
That's where we use something called ARQ techniques, which stands for automatic repeat request.
Okay.
The simplest and maybe the most intuitive is stop and wait ARQ.
Sounds straightforward.
It's exactly what it sounds like. The sender sends one packet, then literally stops and waits. It waits for an acknowledgement, an ACK, from the receiver before sending the next one.
Simple enough. Pros and cons.
Well, it's easy to implement, that's a plus. And it's pretty robust for very noisy channels because each packet is confirmed individually. But as you can imagine, the main drawback is it's incredibly inefficient.
Just painfully slow, I bet. One packet at a time.
Exactly. Painstakingly slow. That's where the ingenuity of sliding window flow control comes in. This is a real game changer for efficiency.
How does that work?
Instead of waiting for an ACK for every single packet, the sender can transmit multiple frames or packets before receiving any acknowledgments. Both the sender and receiver agree on a specific number of frames, the window size that can be in flight simultaneously.
So you keep the pipe full.
Precisely. It drastically improves network throughput. You're essentially keeping the pipeline full of data.
Okay, and you mentioned different flavors of sliding window?
Right. Within sliding window, there's a particular type that really showcases cleverness. Selective repeat protocol, or SR.
Selective repeat. What's special about it?
The brilliance here is that when the receiver detects a corrupted or missing frame, it doesn't just give up on everything that came after it, like some simpler methods do.
Okay.
It actually buffers any out-of-order frames that arrive correctly, and then it sends a specific request, often a negative acknowledgement, an NACK, for only the missing piece.
Just the one it needs.
Just the one. This means the sender only retransmits the single missing frame, not an entire window's worth of data.
Wow. That must be a massive efficiency gain, especially if errors aren't, like, constant, but happen occasionally.
Huge gain. Especially over links where errors are somewhat common, you're not wasting precious bandwidth resending good data that the receiver already has.
Very clever. Is there anything else for efficiency at this layer?
Yes. To squeeze even more efficiency out, especially in two-way communication, we use a neat trick called piggybacking.
Piggybacking, like giving the ACK a ride.
Kind of, yeah. Instead of immediately sending a separate acknowledgement packet every single time data arrives, the receiver waits just a little bit.
Okay. Why wait?
Because if it has its own data to send back to the original sender soon, it delays the acknowledgement slightly and essentially attaches it to its outgoing data frame.
So you combine them.
Exactly. This avoids sending a tiny, dedicated ACK packet, which saves bandwidth and overhead. It's all about minimizing those small, chatty packets.
Makes sense. Okay, so we've got reliability, flow control. What about structure? You mentioned frames earlier.
Right. Beyond managing flow and reliability, the data link layer also needs to give some structure to the raw bit stream coming up from the physical layer. This process is called framing.
Framing. Breaking it up.
Yeah, it's how we break up what could be an endless stream of ones and zeros into discrete, manageable chunks frames. And it's where we add important info like checksums for error detection.
So how do you mark the start and end of a frame, especially if the data itself might look like a marker?
Good question. There are a few methods, but one particularly clever solution, especially when you're dealing with arbitrary bit streams, meaning you don't know what patterns might appear in the actual data, is flag bits with bit stuffing.
Bit stuffing. Sounds interesting.
It really is. Each frame begins and ends with a special, unique bit pattern. The standard is 01111110. That's the flag.
Okay, but what if that pattern appears in my data?
That's the clever part. The sender's data link layer hardware automatically monitors the beta stream. If it sees 5 consecutive ones in the actual data, it automatically stuffs a 0 bit right after them.
It just inserts a 0.
Yep. Then, on the receiving end, the hardware sees 5 consecutive ones followed by a 0, and it automatically plucks out that stuffed 0.
So the receiver just removes it.
Exactly. The whole process is completely transparent to the layers above, but what it achieves is ensuring that the unique flag pattern, the 6 ones in a row, 01111112, can only appear at the actual frame boundaries, never accidentally within the data itself.
That is elegant. Wow. It just works regardless of the data content.
Pretty much. It underpins the flexibility of modern data link layers, allowing them to carry any type of digital information reliably.
Okay, so we've got our data framed nicely, and we know how to make sure it arrives reliably using things like selective repeat and error checks. But here's the next big challenge, right? How do multiple devices actually share the same communication channel, like on Wi-Fi or old-school Ethernet? How do they avoid everything descending into chaos?
Right. Everyone talking at once.
Exactly. This brings us to network topologies, the physical and logical layouts of our networks, and the access methods, which are essentially the traffic rules for sharing that channel.
Let's touch quickly on network topologies, the literal shape of the LAN, the local area network.
Okay.
The simplest, maybe, is the bus topology. You just have devices connecting to a single shared cable, like beads on a string.
Easy to set up, I guess.
Yeah, easy to install initially. But our sources note disadvantages. It can be difficult to add new devices without disrupting everyone, and pinpointing faults, like a break in the cable, can be a real headache.
All right, a break takes down the whole segment.
And signal reflection off the ends can degrade quality too, if not handled properly.
What else?
Another common one is the ring topology. Here, each device connects only to its two immediate neighbors, forming a closed loop.
Seems more structured.
It is. It's relatively easy to reconfigure. Adding or removing a device only changes to specific connections. However, there's a significant drawback, especially if traffic only flows in one direction.
What's that?
A single break in the ring, say a workstation gets turned off or its connection fails, can completely disable the entire network. It's a critical single point of failure for the whole loop.
Ouch. Okay, so those are the layouts. How do we manage this sharing part, the access?
Right. To manage how devices actually share that channel, especially in broadcast networks like Ethernet or Wi-Fi where everyone can potentially hear everyone else, the IE, that's the standards body, did something clever. They subdivided the data link layer into two sublayers.
More layers.
Yep. Logical link control, LLC, and media access control, MAC.
LLC and MPEG, what do they do?
Think of the LLC as the universal translator on top. It handles the general tasks like framing, flow control, error control, providing a consistent interface to the network layer above it, regardless of the underlying network type.
Okay, so it hides the differences.
Exactly. It makes the MA sublayer transparent. The MA sublayer, on the other hand, is where the specifics live. It defines the specific access method for each type of local network.
Like how Ethernet shares versus how token ring shares.
Precisely. CS mass CD for Ethernet, token passing for token ring or token bus. It's where the real rules of sharing the media, are put into play. It also handles part of the framing sometimes.
Gotcha. So this MAC layer is where the battle for the bandwidth happens.
That's a great way to put it. It leads us to multiple access protocols. The absolute pioneer here was Aloha, developed at the University of Hawaii. Incredibly simple idea.
Which was?
Users just transmit whenever they have data, just send it.
What about collisions, if two send at once?
Collisions happen a lot, actually, in pure Aloha. If a frame was destroyed by a collision, the sender would detect that somehow, wait a random amount of time, and then try retransmitting. That random delay was critical to prevent them from just colliding again immediately.
Randomness saves the day.
Sort of. It worked, but wasn't very efficient. A clever improvement was slotted Aloha.
How did that work?
It divided time into discrete slots, and users were only allowed to transmit at the very beginning of a slot.
Synchronized transmission attempts.
Exactly. This simple change effectively halved the vulnerable period during which a collision could occur, and theoretically doubled the maximum capacity compared to pure Aloha. Still not great, but better.
Right, so building on Aloha, what came next?
We got carrier sense, multiple access CSMA protocols. The core idea here is simple. Stations listen before they leap.
Check if the coast is clear.
Right. They sense the channel, the carrier, to see if it's busy before transmitting. Avoids many collisions right off the bat.
Seems logical.
But the real game changer, and the absolute basis for classic Ethernet, was CSMA with collision detection, CSMCD.
Collision detection. That sounds key.
It is. The brilliance here is that stations don't just listen before they transmit, they also listen while transmitting.
So they can hear if someone else started talking at the same time.
Precisely. If a station detects a collision, meaning the signal it's reading back from the channel is different from the signal it's putting out, it immediately stops transmitting.
Abort! Abort!
Exactly. Then it sends out a brief jamming signal to make sure everyone knows a collision happened, waits a random amount of time using a specific algorithm called binary exponential backoff, and then tries the whole process again, listen, transmit while listening.
That listen while transmitting part is what makes Ethernet work so well, isn't it?
It's absolutely key to its efficiency and why Ethernet became so dominant for wired networks.
Okay, but you can't just use CSMCD on Wi-Fi, right?
Yeah.
Our sources mention wireless woes.
Exactly right. You can't simply take CSMED and apply it directly to wireless networks like Wi-Fi. Wireless environments introduce unique challenges that just don't exist on a wire.
Like what?
Well, for example, the hidden station problem. Imagine Station A is transmitting to Station B. Station C might also want to transmit to B. But because of distance or obstructions, C can't hear A's transmission.
So C thinks the channel is free.
Right. C falsely assumes the channel is free and starts transmitting, causing a collision at B, who can hear both.
Nasty. What else?
Conversely, there's the exposed station problem. Let's say B wants to send to C, and nearby, A is transmitting to D. B can hear A's transmission.
So B waits.
Yeah, B hears A and falsely concludes it cannot transmit, even though its transmission to C would likely not interfere with A's transmission to D. It's unnecessarily blocked.
Huh. And didn't you say radios can't listen while talking?
Correct. Most wireless radios are half duplex. They simply can't transmit and listen at the exact same time like an Ethernet card can. That makes CSMB physically impossible for most Wi-Fi devices.
So wireless is tricky. How does Wi-Fi solve this chaos then?
To solve this wireless chaos, Wi-Fi, that's the IEEE 802.11 standard, uses CSMCA, collision avoidance.
Avoidance, not detection? How?
The most common method, called the Distributed Coordination Function, DCF, doesn't rely on any central control. It uses physical sensing, like CSMA, transmit if idle, defer if busy. But it adds a truly ingenious solution called virtual channel sensing, often using RTS-CTS.
RTS-CTS, request to send, clear to send.
Exactly. Here's the magic. If Station A wants to send a chunk of data to B, A first sends a small RTS, request to send message to B. If B is ready, it replies with a CTS, clear to send message.
Okay, like asking permission.
Yes, but here's the key part. Any other stations within range that hear either the RTS, like Station C in the hidden station example, or the CTS message, then set an internal timer. It's called a NAV, Network Allocation Vector.
A timer. What does it do?
The NAV essentially tells that station, keep quiet for the specific duration, which is the time A needs to send its data to B and get an acknowledgement.
Ah, so everyone who might interfere is told to shut up for a bit.
Basically, yes. This preemptive reservation of the channel significantly helps manage both the hidden and exposed station problems. It's collision avoidance, not detection.
Very clever indeed. Okay, switching gears slightly. What about connecting devices over longer distances, not just in a local LAN?
Right. When you think about how devices connect point to point over longer distances, like your home router connecting to your internet service provider, the point-to-point protocol, PPP, is absolutely vital.
PPP, what does it do?
Our sources highlight 3 key features. First, it has a robust framing method, often based on that bit stuffing technique we discussed, to ensure data integrity over the line.
Okay, framing.
Second, it includes a link control protocol, LCP. This is for managing the connection itself, bringing the line up, negotiating options like authentication, testing the line, and eventually tearing it down gracefully.
Connection management.
And third, it uses network control protocols, NCPs. There's usually one NCP for each network layer protocol being carried, like IP. The NCP is responsible for negotiating network layer options specifically for that protocol, like assigning your computer an IP address when you connect via PPP.
Got it. Framing, link management, and network setup.
Pretty much covers the essentials for point-to-point links on the internet.
And for really short distances, like my phone to my headphones.
For those shorter personal connections, there's Bluetooth. That's the IEEE 802.15 standard designed specifically for wireless personal area networks, or PANs.
PANs, okay.
This is exactly how your phone connects to your headphones, or your keyboard, or your car's system. It allows devices to spontaneously form a small network called a piconet.
Piconet.
Yeah. It consists of one master device and up to 7 active slave devices, all coordinated by the master.
7 slaves seems specific.
It is. For active slaves, there can be more parked ones. What's also interesting is how multiple piconets can even link up, with the device being a slave in one and a master in another, to form a scatternet.
Scatternet? Sounds messy.
It can be complex to manage, but it allows for larger interconnected networks. And Bluetooth is designed to handle different types of data, too, like best effort packet data for file transfers, alongside real-time synchronous links for voice calls, each with different reliability needs.
Flexible. Okay, so we have local networks, point-to-point links, personal networks. But what happens when networks grow really big, like across a campus or a large company? You can't just keep extending one single LAN forever, right?
Exactly. Imagine trying to run one giant Ethernet cable across an entire university campus or through a multi-story office building. It becomes impractical due to distance limitations, performance bottlenecks, and just sheer management complexity.
So what's the solution?
This is where bridges come in. Bridges allow us to intelligently connect multiple LANs together. They operate at the data link layer, layer 2.
Layer 2, okay. So they look at MAC addresses.
Precisely. They make their forwarding decisions based on the destination MXE address in the frame header. They're smarter than simple repeaters, which just regenerate signals at the physical layer.
So why use bridges? What are the benefits?
Well, there are several practical reasons our sources highlight. First, connecting separate LANs, maybe different departments that want some autonomy but still need to communicate.
Makes sense.
Second, spanning geographical distances between buildings, connecting LANs that are physically separate. Third, accommodating heavy network load, you can split a busy LAN into 2 less busy segments connected by a bridge.
Improving performance.
Right. Also, increasing the total physical distance the network can cover, improving reliability by isolating failures. If one LAN segment goes down, the bridge stops traffic from propagating, so it doesn't necessarily take the whole network with it.
That's a big one. Reliability.
And enhancing security to some extent by keeping local traffic contained within its own segment unless it's specifically addressed to go elsewhere.
Okay, how do they work? Do you have to configure them manually?
The most common type, and the really clever ones, are transparent bridges. And the beauty is, you usually don't have to configure them manually. They learn.
They learn.
When you first turn them on, they're completely dumb, as our sources put it. They have no idea which device lives on which of their ports or connected LAN segments.
So what do they do with the first packet?
They use a few key mechanisms. First is learning. When a frame arrives on a port, the bridge looks at the source MSE address and notes which port it came in on. It builds up a table, a MAC address table or bridge table, mapping addresses to ports.
Okay, learning by listening.
Exactly. Now, if a frame arrives and the bridge doesn't know which port the destination MSE address is on because it hasn't seen traffic from that address yet, it performs flooding.
Flooding. Sends it everywhere.
Pretty much. It sends the frame out on all its ports except the one the frame arrived on, hoping the destination will see it.
Seems inefficient, but necessary if you don't know.
Right. But once the bridge has learned where a destination MSE address lives, it can perform forwarding. It receives a frame on one port, looks up the destination MSE in its table, and sends the frame only out the correct port leading towards that destination.
Much better.
And there's filtering. If the bridge sees a frame arrive on port 1, and it knows from its table that the destination MC address is also reached via port 1, it just drops the frame.
Because it doesn't need to cross the bridge.
Exactly. The traffic stays local to that segment. And finally, there's aging. Entries in the bridge table don't stay forever. If an address hasn't been heard from in a while, say 5 minutes, its entry is removed. This allows the bridge to adapt if devices are moved or turned off.
Learning, flooding, forwarding, filtering, aging. That's quite smart for something transparent.
It is. But there's a potential major pitfall when you connect multiple LANs with multiple bridges.
What's that?
Loops. Imagine you have 2 LANs connected by 2 different bridges, creating a redundant path. A broadcast frame sent on one LAN could get forwarded by both bridges to the other LAN, then back again by both bridges, circulating endlessly.
Oh, wow. A broadcast storm that would kill the network.
Instantly. Consumes all your bandwidth, pegs the bridge CPUs, it's catastrophic. This is where spanning pre-bridges, using the spanning tree protocol, STP, come in. Their brilliance lies entirely in solving this loop problem.
Spanning tree. Sounds mathematical.
It kind of is. They automatically collaboratively build a logical spanning tree across the bridge network. Essentially, they figure out a configuration where there is only one active path between any 2 LANs, thereby preventing loops.
How do they do that?
It involves the bridges electing one bridge as the root of the tree. Then each bridge calculates the shortest path back to the root bridge. Based on these calculations, certain bridge ports are designated as forwarding ports, part of the active tree, while others might be put into a blocking state.
So they temporarily disable redundant links.
Exactly. Those links are still physically there, ready to take over if an active link fails, but they don't forward regular data traffic in the meantime, thus breaking any potential loops. The algorithm constantly runs in the background, exchanging special messages, BPDUs, to detect topology changes and automatically reconfigure the tree if, say, a bridge or a link fails.
That's critical. Automatic loop prevention and redundancy.
Absolutely. It's an elegant and essential solution for building robust, larger switched networks.
Okay, so bridges handle connecting LANs at layer 2. Now let's zoom out even further. From the local street, maybe, to the entire highway system of the internet.
Good analogy.
The network layer. This is layer 3. This is the first layer that truly thinks end-to-end, isn't it? Responsible for getting a packet from its original source all the way to its final destination, even if that means crossing many, many different networks and routers along the way.
That's right. It's all about finding the best path through a potentially vast and constantly changing landscape of interconnected networks.
So what are the key design issues here at the network layer?
Well, a fundamental mechanism is store and forward packet switching. This is different from, say, an old telephone circuit where you had a dedicated connection.
How so?
Here, a router receives a full packet, stores it temporarily in memory, usually verifies its header checksum to check for errors, looks up the destination address in its routing table to decide the next hop, and then forwards the packet out the appropriate interface towards that next hop.
Store, verify, forward. Why do it that way?
It ensures data integrity at each hop, at least for the header. More importantly, it decouples the links. The router can receive a packet from a slow link and send it out on a fast link, or vice versa. And it allows the router time to make that crucial routing decision: where does this packet go next?
Makes sense. And what services does this network layer provide to the layer above it, the transport layer?
The goals here are generally independence from the underlying router technology, shielding the transport layer from the messy details of the network topology, and providing a uniform addressing scheme that works across the entire internetwork. There are two main philosophical approaches to the service model: connectionless and connection-oriented.
Datagrams versus virtual circuits.
Exactly. Connectionless service, like the internet's IP, treats each packet or datagram independently. Each one is routed based on its destination address, and they might take different paths or even arrive out of order. Connection-oriented service, more like ATM networks, sets up a dedicated path, a virtual circuit, before data transfer begins. All packets for that connection follow the same path.
Okay, so routers are making these path decisions. That means they need routing algorithms, right? The router's brain.
Absolutely. At the heart of the router's brain are the routing algorithms. Before we dive into specific ones, there's a really interesting foundational idea called the optimality principle.
Optimality principle, what's that?
It states something that sounds almost obvious, but has big implications. If router J is on the optimal path from router I to router K, then the optimal path from J to K must also follow that same route.
Okay. Yeah, that makes sense. If there was a better path from J to K, then the path from I to K wouldn't have been optimal in the first place.
Precisely. This principle implies something powerful. The set of optimal routes from all sources to a given destination actually forms a tree rooted at that destination. We call this a sync tree. The goal of all routing algorithms, then, is essentially to discover and use these sync trees for each destination.
Find the best tree for each destination. How do they do that?
Well, one of the classic algorithms for finding shortest paths in a graph, which is what a network looks like to a router, is Dijkstra's algorithm.
Dijkstra, I've heard of that one. How does it work, basically?
It's quite methodical. It iteratively discovers the shortest path from a starting node, say your own router, to all other nodes in the network graph. It keeps track of nodes whose shortest path is definitely known, permanent, and those whose path is still tentative. At each step, it looks at all the tentatively labeled nodes, picks the one with the minimum current cost, distance from the source, makes its label permanent, and then updates the tentative costs of its direct neighbors, seeing if reaching them via this newly permanent node creates a shorter path than previously known.
So it grows outwards from the source, locking in the closest nodes first.
That's a great way to visualize it. It systematically explores the network, always locking in the next closest node until it has found the shortest path to every other node. It requires knowing the entire network topology map, though.
Okay. What other ways are there to route?
Well, there's flooding. It's simple, maybe even crude, but surprisingly robust.
Flooding, just send it everywhere.
Pretty much. Every incoming packet is sent out on every outgoing line except the one it arrived on.
Wow, that sounds noisy.
It is. The advantages are that it's highly robust. If there's any path, flooding will find it. Great for military networks or distributed databases where reliability is paramount. It also always finds the shortest path because it inherently tries all possible paths in parallel, effectively, and it's useful for broadcasting information quickly.
But the downsides must be huge.
Oh, yeah. Massive duplication of packets. It generates an enormous amount of traffic and wastes bandwidth like crazy. You absolutely need mechanisms to control the flood.
How do you stop the flood?
Usually with things like a hop counter in the packet header, each router decrements it, and if it hits 0, the packet is discarded. Or routers can keep track of sequence numbers for packets they've already seen from a particular source and discard duplicates.
Okay, so flooding is one extreme. What's more common?
More common, especially in the early internet and smaller networks, was distance vector routing, sometimes called the whisper network or routing by rumor.
Why those names?
Because routers using this only talk directly to their immediate neighbors. Each router maintains a table, its vector, which lists the best known distance, like hop count or delay, to every other destination in the network, and which neighbor outgoing line to use to get there.
Okay, just distance and next hop.
Right. And they update these tables periodically by exchanging their entire distance vector table only with their direct neighbors. A router receives tables from its neighbors, adds its own cost to reach that neighbor, and then updates its own table if a neighbor offers a shorter path to some destination.
So it learns about the wider network only through what its neighbors tell it.
Exactly. It computes its new table based only on the information received from its neighbors and its own directly measured cost to reach those neighbors. Common examples were RIP, Routing Information Protocol.
Seems simple enough. Are there drawbacks?
Oh, yes. There's a critical and, frankly, quite problematic challenge with distance vector routing, the notorious count to infinity problem.
Count to infinity, that sounds bad.
It is. It highlights how bad news travels slowly in this type of algorithm. Imagine a direct link between router A and router B goes down. Router A knows immediately its distance to B is now infinite, or very high.
Okay.
But maybe router C used to route to B via A. Router A tells C the path is gone. But what if router D also used to route to B via A, and router C hears from router D before it processes A's update? D might still be advertising a path to B, an old invalid one. C might think, oh, D has a path to B, and update its own route to go via D.
Creating a loop?
Yeah.
C points to D. D might point back to C indirectly?
Exactly. Because a router doesn't inherently know the full path its neighbor is advertising, just the distance, it can get caught in these loops when a link goes down. The distance estimates for the downed link will slowly increment. C increases its cost, tells D, D increases its cost, tells C, and so on, gradually counting up to infinity, usually a predefined maximum hop count like 16 for RIP, before the network finally stabilizes and realizes the destination is unreachable.
Wow. So convergence after a failure can be incredibly slow and problematic.
Very slow, especially for bad news. Good news, like a new link coming up, propagates much faster.
Okay, there must be a better way.
There is. To overcome these problems, especially count to infinity and the fact that simple hop count doesn't factor in link speed or congestion, link state routing was developed. Think of these routers as map builders.
Map builders, how does that work?
Instead of just whispering distances to neighbors, link state routers follow a 5-step process. First, they discover their neighbors, usually by sending simple hello packets.
Okay, find out who's directly connected.
Second, they measure the line cost to each neighbor. This could be delay, measured with echo packets, or configured based on bandwidth, or even factor in current load.
Get a cost metric for each link.
Third, each router builds a link state packet, LSP. This is a small packet containing its own identity, a sequence number, an age, and then a list of its neighbors with the measured cost to each one. Basically, here's who I am and who I can reach directly and at what cost.
Okay, a packet describing its local connections.
Fourth, and this is crucial, they distribute these LSPs to all other routers in the routing domain. This is typically done using controlled flooding, but with sequence numbers and an age field to prevent duplicates and handle old information gracefully. If an LSP's age hits 0, it's discarded, helping to clear out info from crashed routers.
So everyone gets everyone else's LSP.
Eventually, yes. Which leads to the 5th step. Compute new routes. Once a router has received all the LSPs from all other routers, it can assemble them to construct the entire subnet graph, the complete map of the network, right there in its own memory.
Wow, a global view.
Exactly. And with the complete map, it can then run Dijkstra's algorithm locally on that map to compute the shortest paths from itself to all other destinations.
Ah, so Dijkstra comes back, but now applied to the full map learned via LSPs.
Precisely. This approach gives every router a consistent global view of the network topology and costs. This leads to much faster and more accurate convergence, especially when network conditions change, and it avoids the count to infinity problem entirely because loops are implicitly prevented by building the shortest path tree from the known map. OSPF and ISIS are common examples.
That sounds significantly more robust. Okay, what about specialized routing, like for devices that move around?
Right. Routing for mobile hosts. Imagine the challenge. How do you send a packet to a device, like your phone or laptop, that's constantly moving between different networks? Its IP address is usually tied to its home network.
Yeah, how does that work? Does it get a new IP everywhere?
Not necessarily. That would break ongoing connections. The standard solution is quite clever, using a kind of home away from home system. Every mobile host is associated with a home agent, which is a router on its designated home network.
Okay, a fixed point of contact.
Yes. When the mobile host travels and connects to a different network, a foreign network, it registers its current location, its temporary care of address, with a foreign agent in that new location. The foreign agent is typically a router on the network being visited.
So it checks in.
It checks in. The foreign agent then informs the home agent, hey, your mobile host is currently over here at this care of address.
Okay, the home agent now knows where it is.
Now, when someone sends a packet addressed to the mobile host's permanent home address, the packet naturally arrives at the home network. The home agent intercepts it.
Intercepts it.
Yeah, it grabs the packet and says, aha, this host isn't here, it's over there. Then the home agent tunnels the packet.
Tunnels, like puts it inside another packet.
Exactly. It encapsulates the original packet inside a new IP packet addressed to the foreign agent's care of address. The foreign agent receives this outer packet, decapsulates it, finds the original packet inside, and delivers it local to the mobile host.
Wow, so the original sender doesn't even need to know the host moved.
Initially, no. The home agent handles the redirection. For optimization, the home agent can then inform the original sender of the mobile host's current care of address, so subsequent packets can potentially be tunneled directly to the foreign agent, bypassing the home agent, though the HA usually remains involved for control. It's a system designed to make mobility pretty seamless from the outside.
Clever indirection. What about sending to a group? You mentioned multicast.
Right, multicast routing. This is all about efficient one-to-many communication. The goal is to send a single message from one source to a defined group of destinations simultaneously. Think about streaming a live video conference to a specific set of participants or distributing stock quotes to interested subscribers.
You want to send individual copies to everyone?
Definitely not. That's unicast flooding, basically. And you don't want to broadcast it to the entire network if only a small group cares. That wastes bandwidth everywhere else.
So how does multicast routing work?
The core idea is usually based on spanning trees again. Routers first compute a spanning tree covering the relevant parts of the network. Then, for a specific multicast group address, they prune this tree.
Prune it? Like trimming branches?
Exactly. They effectively cut off branches of the tree that don't lead towards any network segments where there are members registered for that specific multicast group.
So the multicast packet only travels down the branches that actually have interested listeners.
Precisely. This ensures the message is delivered efficiently only to the networks containing interested recipients, avoiding unnecessary traffic flooding across the rest of the internetwork. Protocols like PIME, Protocol Independent Multicast, manage this process.
Okay, so routing gets the packets where they need to go. But how do networks, manage themselves? How do they report problems or figure out addresses? Is there more going on besides just forwarding?
Absolutely. This raises an important question. How do networks manage themselves and respond when things go wrong? Beyond simply routing data packets, there's an entire suite of control and management protocols constantly working behind the scenes. Think of it like the nervous system and the address book of the internet, keeping things functioning, troubleshooting issues, and enabling those crucial address mappings.
Okay, like what? What's in this toolkit?
First up, and really fundamental, is ICMP, the Internet Control Message Protocol. It basically acts as the Internet's troubleshooter and messenger service at the network layer.
ICMP, I think Ping uses that, right?
Exactly. The classic ping command uses ICMP. You send an ICMP echo request message to a destination, and if it's reachable and configured to respond, it sends back an ICMP echo reply.
This is a basic, are you there? Check.
Yep. Simple but fundamental proof that IP communication is working end-to-end between those two systems. But ICMP does much more. It's also used for error reporting.
Like what kind of errors?
For instance, our router might send back an ICMP destination unreachable message if it doesn't know how to get to the destination address, or if a firewall blocks the packet. Or maybe an ICMP time exceeded message if a packet's time to live, TTL, counter hits 0, which usually indicates a routing loop or excessive congestion.
The TTL field prevents packets from circulating forever.
Right. ICMP is the mechanism that reports back when TTL expires in transit. There are other messages too, like parameter problem if there's something wrong with a packet header, or redirect, where a router tells a host it's using a suboptimal path and suggests a better next hop router on the same local network.
So it's like the network's way of sending little status updates and error notices back to the source.
That's a good way to think about it. It's crucial for diagnosing problems.
Okay, diagnostics. What about that address mapping problem you mentioned earlier? Layer 3 IPs versus Layer 2 MSC addresses.
Right. This is a big challenge, especially on local networks like Ethernet or Wi-Fi. Every machine has a logical IP address, layer 3, but the actual data link layer hardware, the network card, only understands physical hardware addresses, the MSC addresses, layer 2. So when your computer wants to send an IP packet to another computer on the same local network, how does it figure out the destination MSC address needed to actually transmit the frame?
Yeah, how does it get the MAC?
This is where ARP, the address resolution protocol, comes in. It's like the local network's decoder ring or directory assistant.
How does it work?
When a device, say host A, wants to send an IP packet to host B on the same LAN, but doesn't know host B's MAC address, host A broadcasts an ARP request packet onto the local network. This broadcast essentially shouts out, who has the IP address 192.168.1 typed in? Please tell me, host A, at address AAEBCC.
So everyone on the LAN sees this request?
Yes, but only host B, the actual owner of IP address 192.168.1200, should respond. Host B sends back a unicast ARP reply directly to host A saying, hey, I have that IP address and my MAC address is DDEF.
So host A gets the MC it needs. Does it have to do this every single time?
No, that would be inefficient. Devices maintain an ARP cache, which is a temporary table storing recent IP to MAC address mappings they've learned. So the next time host A wants to send to host B, it checks its cache first. If the entry is there and hasn't expired, it just uses the cached MPass address. No broadcast needed.
Smart.
Yeah.
Caching saves broadcast.
Definitely. And there's another clever trick called proxy ARP.
Proxy ARP, like ARP acting on behalf of someone else.
Exactly. A router can be configured to respond to ARP requests for IP addresses that are not on the local network segment, but are reachable through that router.
Why would it do that?
Imagine host A sends an ARP request for host C, which is on a different network connected via router R. Normally, ARP is local, but if router R is configured for proxy ARP, it sees the request for host C's IP and replies with its own MC address, the one on host A's network.
So host A thinks router R is host C at the MSC layer.
Kind of. Host A just knows that to reach host C's IP, it should send frames to router R's MC address. Router R then takes care of forwarding the IP packet towards the real host C. It makes remote hosts appear as if they're on the local network, which can simplify routing configurations for simple hosts that don't understand subnets well.
Interesting trick. Okay, so ARP gets MAC from IP. What about the other way around? If a machine only knows its MAC?
The reverse problem. That used to be handled by our reverse address resolution protocol. This was mainly for things like diskless workstations that knew their own hardware MA strings but needed to find out their assigned IP address when they booted up.
Used to be. Is it obsolete now?
Largely, yes. RRP had limitations, the requests were broadcast, and typically didn't cross routers, meaning you needed a RRP server on every single network segment. It wasn't very practical.
So but what replaced it? How do devices get their IP addresses now when they boot up?
The modern solutions are BOATP, Bootstrap Protocol, and especially its successor, DHCP, Dynamic Host Configuration Protocol. These are much more sophisticated.
BOTP and DHCP.
BOATP was an improvement over RARP. It's a client-server protocol, still for mapping a physical address to an IP address, but it operated at the application layer and, crucially, used relay agents. These agents allowed BOATP requests, which are broadcasts, to be forwarded across routers to a central BOATP server. However, BOATP was primarily for static configuration. The server had a pre-configured table mapping specific ME addresses to specific IP addresses.
Static, so not very flexible for large networks.
Right, which brings us to DHCP. This is a workhorse for IP address assignment today. It's the modern successor to BOATP and is largely backward compatible. The huge advantage of DHCP is that it provides dynamic IP address allocation.
Dynamic, like temporary addresses.
Exactly. Instead of just static assignments, a DHCP server manages a pool of available IP addresses. When a new device joins the network and sends out a DHCP request, the server can dynamically assign it an available IP address from the pool for a specific period, called a lease time.
The lease. So addresses get reused when devices leave.
Precisely. DHCP can still do static assignments if needed, called reservations, but the dynamic allocation is what makes it so scalable and essential for modern networks. Think about connecting your laptop at a coffee shop. DHCP is what gives you that temporary IP address. It can also provide other crucial configuration info like the subnet mask, default gateway router address, and DNS server addresses.
So DHCP is really fundamental to how you just connect and go online today.
Absolutely critical. Okay, what about routing between these big networks, the autonomous systems we mentioned?
Right, the countries of the internet, how do they coordinate?
That's where BGP, the Border Gateway Protocol, comes in. BGP is the standard interdomain routing protocol. Its job is specifically to exchange routing information between different autonomous systems, ACs. It's not typically used within an AS. That's where protocols like OSPF or ISCS run.
So BGP is the glue that holds the internet's routing together at the highest level.
Exactly. It's all about reachability information between these large networks. And critically, it's heavily driven by policy, not just shortest paths.
Policy? What do you mean?
An AS might have agreements with its neighbors about what kind of traffic it's willing to carry, or which paths it prefers for cost or business reasons. BGP allows administrators to implement these complex routing policies. For example, an AS might refuse to carry traffic that's just passing through between two other ACs, or it might prefer sending traffic via a cheaper link, even if it's slightly slower.
So it's not just about finding any path, but the agreed upon or preferred path based on rules.
Precisely. Our sources typically categorize ACs based on these policies. A stub AS has only one connection to another AS. Traffic originates or terminates within it, but it doesn't pass through to connect other ACs.
Okay, an endpoint network.
Then there's a multi-homed AS, which has connections to multiple other ACs, usually for redundancy or performance. But like a stub AS, it generally doesn't allow transient traffic just passing through either.
Got it. Connected to many, but still mostly an endpoint.
And finally, there's the transit AS. This is typically a multi-homed AS that does allow transient traffic to pass through it, connecting other ACs together. These are your major internet service providers, the big backbones of the internet.
So BGP is managing these complex policy-based routes between all these different types of ACs, basically deciding how data flows across the globe.
That's a very good summary. It's a complex but vital protocol that scales to the size of the entire internet, making decisions based on reachability, path attributes, and administrative policies.
Wow. Okay. So we've talked a lot about how the internet works now, largely based on IPv4, the addressing scheme we've used for decades. But IPv4 addresses are running out, right?
They essentially have, yes. Although clever techniques like NAT, network address translation, have extended its life significantly. But the fundamental limitation of a 32-bit address space became clear a long time ago.
Which led to the need for an upgrade. This is where IPv6 comes in, right? The next generation internet protocol.
Exactly. IPv6 was designed specifically to address the limitations of IPv4, primarily the address exhaustion issue, but also to bring other improvements.
So what are the main advantages of IPv6?
The most obvious and arguably the most critical advantage is its vastly larger address space. We're talking about a massive leap from IPv4's 32-bit addresses, about 4.3 billion, to 128-bit addresses in IPv6.
128 bits, how many addresses is that?
It's astronomical, 2 to the power of 128. That's roughly 340 undecillion addresses. Enough to assign a unique IP address to practically every atom on the surface of the Earth, and then some. Address exhaustion is simply not a concern with IPv6.
Okay, problem solved there. What else does it offer?
It features a streamlined header format. Some fields from the IPv4 header were removed or moved to optional extension headers. This simplifies the main header and potentially speeds up packet processing in routers.
Faster routing. Okay.
It also has new options and extensions designed for better future flexibility and adaptability. There's built-in support for resource allocation using a flow label field, which allows sources to request special handling for certain packet streams, like real-time video or audio, potentially improving quality of service.
Built-in QoS hints.
Kind of. And importantly, it was designed with more security in mind from the start. Features like IPsec for encryption and authentication are integrated more fundamentally into the IPv6 architecture rather than being an add-on as they often were with IPv4.
Okay, more addresses, simpler header, better options, QoS, security. Sounds like a solid upgrade. How do the addresses themselves look? They must be long.
They are long. An IPv6 address is 128 bits, typically written as 8 groups of 4 hexadecimal digits, separated by colons.
Hexadecimal colons example.
Sure. Something like 2001.0 dB 8.85, 8.000.8000.882e.0370.7334.
That's quite a mouthful.
It is, but there are rules for abbreviation to make them more manageable. You can omit leading zeros within any 16-bit group, so 0db8 stays db8, and 0370 becomes 370. And even better, a single consecutive run of all zero groups can be replaced with a double colon.
Ah, the double colon. So that example could shrink.
Yes, 2001.0db8.85.0.82e.82e.0370.7334 could become 2001 db8.85a3.ate.u370.7334. You can only use the double colon once in an address, though. Otherwise, it becomes ambiguous how many zero groups it represents.
Okay, abbreviation helps. What about ICMP? Did that get an upgrade too?
Yes, there's ICMP v6. It's essentially a revised version of ICMP adapted for IPEZ 6. Interestingly, ICMP v6 takes on some functionalities that were handled by separate protocol for multicast, are now integrated into ICMP v6 using specific message types like neighbor solicitation advertisement and multicast listener query report.
It streamlines things a bit at the network layer.
It does. Some old ICMP messages were removed too, like source quench, which wasn't very effective anyway, and new ones were added, like packet too big, because fragmentation works differently in IPv6. Routers generally don't fragment packets anymore. If a packet is too big for a link, the router sends this message back to the source, telling it to send smaller packets.
Interesting. The source has to handle fragmentation.
Right. Puts more responsibility, but potentially more intelligence at the endpoints.
Okay, so we have these packets flying around IPv4 or IPv6 routed across networks. But what happens when things get too busy? When the network gets overloaded?
Yes. This raises a critical question. How do we prevent network gridlock, especially as data traffic continues to explode? This brings us to congestion control and quality of service. QoS.
Congestion control and QoS. What's the difference?
Congestion control is primarily about managing network overload to prevent performance collapse. It's about keeping the network stable when demand exceeds capacity. Quality of service, on the other hand, is about providing differentiated performance levels to different types of traffic based on their needs.
Okay, avoiding collapse versus providing specific service levels. Let's start with congestion. What causes it?
The basic problem of congestion arises when routers or links receive packets faster than they can process or forward them. Buffers fill up, packets get delayed significantly, eventually packets start getting dropped.
Like too many cars trying to merge onto a highway at once.
Exactly. Factors include simply too high a packet arrival rate, insufficient memory in routers, leading to buffer overflows and packet loss, bursty traffic patterns, sudden floods of packets, slow processors and routers, or just low bandwidth links creating bottlenecks.
And you said congestion control is different from flow control.
Yes, it's important to distinguish. Flow control, which we discussed way back at the data link layer and also exists at the transport layer, like TCP's sliding window, is typically a point-to-point mechanism between a specific sender and receiver to prevent the sender from overwhelming the receiver. Congestion control is a global issue concerning the state of the entire network or subnet multiple sources contributing to overload at shared routers and links.
Got it. Point-to-point versus network-wide. So how do networks try to control congestion?
There are various approaches, often categorized as open loop, trying to prevent it proactively through good design, and closed loop, reacting to congestion once it starts to occur. The closed loop techniques rely on feedback.
Feedback from the network. How?
One early idea was the warning bit. A router experiencing congestion could set a specific bit in the header of packets passing through it. The destination would see this bit and echo the warning back to the source in its acknowledgement packets, prompting the source to slow down.
Simple hint. What else?
More direct is using choke packets. A router feeling congested could generate a special separate choke packet and send it directly back to the source host of the packet that triggered the congestion detection. This packet explicitly tells the source to reduce its transmission rate by a certain amount.
To direct slow down message.
Right. But sending it all the way back to the source takes time, and the source might send many more packets before the choke packet arrives. A variation is hop-by-hop choke packets.
Hop by hop. How does that work?
Here, the choke packet doesn't just go to the source. It takes effect at every router it passes through on its way back. Each intermediate router sees the choke packet, reduces its own flow towards the congested router, and forwards the choke packet upstream. This provides faster relief closer to the point of congestion, but requires more state and processing at intermediate routers.
Interesting trade-off. What if things get really bad and buffers are just overflowing?
When push comes to shove and buffers are completely full, routers have no choice but to resort to load shedding. They simply start discarding packets.
Dropping them on the floor.
Yep. The question then becomes which packets to drop. Our sources mention different policies. You could follow a wine policy, keep older packets, discard new ones. This might be good for file transfers where older data is needed to fill gaps.
Keep the vintage stuff.
Or you could follow a milk policy, throw away older packets, keep the newer ones. This might be better for real-time applications like voice or video, where fresh data is more valuable and late data is often useless anyway.
Keep it fresh. Are there smarter ways than just dropping when full?
Yes. A more proactive and widely discussed approach is random early detection, RED, or variations like WRED, weighted red.
Random early detection?
Yeah.
Sounds preemptive.
It is. Routers using RED monitor their average queue length. Instead of waiting until the buffer is completely full, they start randomly dropping packets before that point, once the average queue length exceeds a certain minimum threshold. The probability of dropping a packet increases as the average queue length grows towards a maximum threshold.
So it signals congestion early and somewhat randomly.
Exactly. The randomness helps avoid global synchronization where all flows back off at the exact same time. By dropping packets early, it aims to signal congestion to TCP senders, who interpret packet loss as congestion, sooner, prompting them to reduce their sending rate before the router's buffer completely overflows. It's a more graceful way to manage incipient congestion.
Okay, so that's managing overload. What about the other side? Quality of service. Making sure my video call works well.
Right. Quality of service, QoS, is about providing predictable or tailored network performance for different applications or flows. A flow is just a sequence of packets from a source to a destination that requires a certain type of service.
The QoS is defined by what? Speed, reliability.
Typically by a combination of parameters. Our sources mention 4 key ones: reliability, likelihood of packets being lost or corrupted; delay, how long it takes a packet to travel end-to-end; jitter, the variation in packet arrival times consistency is key for real-time apps; and bandwidth, the data rate the flow needs.
Okay, reliability, delay, jitter, bandwidth. And different apps care about different things.
Wildly different things. Think about it. A file transfer, like FTP, needs very high reliability. You can't lose bits of your file, but it can usually tolerate quite a bit of delay and jitter.
Right, as long as it gets there eventually and correctly.
Exactly. Now, contrast that with real-time audio or video conferencing. You need low delay and, critically, very low jitter. Packets arriving erratically makes the voice choppy or the video stutter. You need relatively high bandwidth, but you might be able to tolerate a tiny bit of packet loss. The codecs can sometimes hide minor errors.
Totally different priorities. So how do networks actually achieve good QoS for these different needs?
There's a whole toolkit of techniques. The simplest but often most expensive approach is just over-provisioning.
Just throw bandwidth at the problem.
Basically, yes.
Yeah.
Build the network with so much excess capacity that congestion rarely happens and performance is generally good for everyone. Simple but costly and not always feasible.
What?
Buffering at the receiver end can help smooth out jitter, which is crucial for streaming audio and video. By delaying playback slightly to fill buffer, you can absorb variations in arrival time. But the trade-off is increased overall delay.
Okay, buffering helps jitter but hurts delay.
Right. Then there's traffic shaping. This is usually done at the source or network edge to regulate the average rate and, importantly, the burstiness of data transmission. It smooths out traffic flow before it hits the network.
Shaping the traffic flow.
How? 2 classic algorithms are mentioned: the leaky bucket and the token bucket. The leaky bucket is quite rigid. Imagine a bucket with a hole in the bottom. Water packets arrive and fill the bucket. Water leaks out the hole, packets are transmitted at a constant rate. If water arrives too fast and the bucket overflows, the excess water packets is simply lost, discarded. It enforces a strict average rate and limits burst size.
So it smooths traffic but can discard packets if the source bursts too much.
Correct. The token bucket algorithm is more flexible and generally preferred. Imagine a bucket being filled with tokens at a constant rate. To transmit a packet, you need to take a token from the bucket. If the bucket is empty, you have to wait for a token.
Okay, tokens enable transmission.
Here's the key difference. If the token bucket fills up with tokens because the source isn't transmitting, new tokens are simply discarded. But the packets themselves are never discarded by the token bucket mechanism. They just get queued until a token is available.
So it limits the average rate, by the token generation rate, but allows for bursts.
Exactly. Because you can save up tokens up to the bucket size, you can send a burst of packets larger than the average rate as long as you have enough tokens saved up. This makes it much more flexible for handling naturally bursty traffic while still controlling the long-term average rate.
Token bucket seems more useful then. What other QoS tools are there?
There's resource reservation, where applications can explicitly request and reserve network resources like bandwidth, buffer space, or router CPU cycles along a specific path to guarantee the capacity they need. Protocols like RSVP, Resource Reservation Protocol, were designed for this, often used in multicast scenarios where receivers initiate the reservation.
Like booking a lane on the highway?
Kinda, yeah. Related to this is admission control. When a new flow wants to start and requests certain resources, the network, usually edge routers, decides whether to admit the flow based on its requirements and the network's current load and existing commitments. If admitting the flow would jeopardize existing guarantees, it gets rejected.
Gatekeeper function.
Right. And once flows are admitted, packet scheduling algorithms in the routers determine which packet to send next when multiple queues are waiting. Simple FIFO, first in, first out, treats everyone equally. Priority queuing gives strict preference to high-priority traffic. Weighted fair queuing, WFQ, tries to give each flow a fair share of the bandwidth based on assigned weights.
Lots of ways to manage queues.
And finally, a more scalable approach than per-flow reservations is differentiated services, DiffServ. This provides coarser-grained service differentiation. Traffic is classified into a small number of service classes at the network edge, marked with a specific code, DSCP, in the IP header. Core routers then apply different forwarding behaviors. For example, priority levels, different drop probabilities under congestion, based solely on this code without needing per flow state.
Like having different classes of service on an airline.
Exactly. You might have an expedited forwarding EF class for premium low latency traffic and several assured forwarding AF classes with different priority levels and drop preferences. It's a way to provide scalable QoS across large networks.
Wow. Okay. Oh, we've covered a tremendous amount of ground today. Seriously, from the tiniest bits being framed for local delivery all the way up to BGP coordinating routes across the global internet and QoS trying to keep everything running smoothly.
We really have. It's a lot to take in.
So what does this all mean for you, the listener, the person just trying to, use this amazing digital world every day?
Well, connecting all these dots, I think it means that beneath every single click, every video call, every message you send, there's this astonishingly complex, incredibly intelligent, and constantly evolving system hard at work.
It's almost invisible most of the time.
Completely invisible. The simplicity you experience as a user totally belies the ingenious solutions engineers have devised over decades. Solutions to manage errors on imperfect lines, to prevent congestion gridlock, to find the optimal paths across continents in milliseconds, and to handle this ever-increasing diversity of devices and communication needs.
Understanding even a bit of these underlying mechanisms really gives you a completely new appreciation for the digital world, doesn't it?
It absolutely does. You start to see the magic behind the curtain.
It really makes you realize that the seamless experience we often just take for granted is the result of layers upon layers, literally, of carefully designed protocols and algorithms, all constantly making decisions faster than we can blink.
Yeah. Billions of decisions every second, worldwide.
Think about this for a moment. The next time you make a video call, maybe to someone far away, just consider the incredible dance that's happening. The data link layer, framing your voice and video into packets. The network layer, intelligently routing those packets through who knows how many different autonomous systems using protocols like BGP, maybe link state within those systems, all while traffic shaping and QoS mechanisms try to ensure smooth delivery. It's just amazing that it works at all, let alone in real time.
It truly is a modern marvel of engineering.
So here's something to think about. What stands out to you the most about how these complex distributed networks manage to pull off such a remarkable feat of coordination and delivery every single second across the entire globe?